In the last video, we solved our first differential equation using a technique called separation of variables. In this video, we're going to use that same technique to solve a problem related to pollution leaving a lake. So let's get into it. Oftentimes, when you first learn how to solve differential equations, or we're just learning about differential equations, the tricky part, or at least the first tricky part, is setting up the equation itself. It can be very valuable whenever we first start looking at a problem that seems complex to first clear our minds of any notions about the situation that we might have so that we don't start making unnecessary assumptions. So in that sense, being very vague and being very general is actually your ally, just like a politician. So what are we going to do? First, we need a scenario to apply this vagueness to, and I'm going to give you one. So let's say you're in a beautiful and serene environment and you have a nice lake right near you, and for some reason someone thinks it's a great idea to dye it, green for St. Patty's Day or something. At what point in time will those beautiful waters return and all this green murky stuff leave? So if you live next to a lake, you'll notice that typically there's streams feeding the lake and streams leaving the lake. So in that regard, we could look at the lake as a container that holds water, and water flows into it, water flows out of it. But because that's a container, we can say that the water kind of overflows from it. And if there's no water flowing into it, there's no water flowing out of it. We could simulate that like a cup sitting there that's completely full to the very top. Now, not all lakes have an inflow like that and an outflow. Some of them just have an inflow. If that's the case, then we could just say the pollution is going to stay there so long as it doesn't sink to the bottom or float on the top, and we have no way of separating it, and no microorganism is going to eat it, and no sunlight is going to destroy it. So it's trapped there. So now that we've cleared our mind of any assumptions that those things might happen, let's go ahead and get started. We're going to assume next that we have a lake that has an inflow and an outflow, as most do. Then in the next video, we're going to look at seasonal changes of that inflow and outflow and simulate something like that in several different ways. So to show you what kind of problem we're facing, I've created a little simulation in which I have a cup in which I've poured dye into, in this case red, not green. And I'm going to just pour in water, and it's going to be overflowing from there as a lake would overflow. I'm going to do my best to keep the rate fairly constant. The water going in at a specific rate is going to be the water coming out at that same rate. So I begin pouring. Then you could immediately see that, of course, water's flowing outward. We see that it mixes in pretty well to the point where by the time it's coming out, it seems as though it's thoroughly mixed. We can also see that all this is doing is diluting the pollutant and transferring the problem somewhere else. So let's develop our mathematical setup. We saw when we added water, we diluted the pollutant. So we know that the volume of water is important. And we'll include that by saying we have the amount of pollutant distributed through the entire volume. So let's call the amount of pollution P, and the amount of water in the cup, V. So the concentration would then be P divided by V. If we measure V in milliliters, we could say we have some amount of pollution per milliliter. Let's first break the time intervals into seconds, so we can think about it kind of how we thought about the dice game from the previous two videos. So in the first second, let's say a certain amount of water flows in and out. That amount is R. We have R milliliters of water leave, and each milliliter has a certain amount of pollution in it. So we expect the amount of pollution in the cup to drop. In what way? Well, there's R many milliliters, and each milliliter has some amount of pollution, which is P divided by V. So the amount of pollution that left was going to be R, the amount of milliliters we're removing in that 1 second, multiplied by P divided by V, which is the amount of pollution per milliliter. We're taking away R milliliters, we're taking away R times P over V pollution. So R times the concentration. And it's decreasing, so it's a negative. The concentration drops the next second when we repeat the same thing. So each second by second, the concentration itself is going to change. Because we're dealing with discrete steps, we get our difference equation, delta P divided by delta T is equal to negative R times P divided by V. So let's do a quick check to make sure our equation makes sense. If we're measuring the pollution in grams, and we're measuring its change every second, then the end result should be that it's changing in some grams per second. So if we look at the equation, we have R, which is a milliliters per second, multiplied by a concentration, which is grams per milliliter. The units of milliliters cancel out, and we get grams per second is equal to the change in pollution. And that makes sense. We then use calculus to take the limit of those discrete steps so that they become smaller and smaller to give us our differential equation, which is going to be dP dt, the amount of pollution that's changing, is equal to negative R times P divided by V. Let's go ahead and solve this. First, we move the dt to the other side. Then we move the P to the other side as well. Then we shift things around a bit. Then we integrate both sides. The left-hand side gives us the log of P plus some constant, and it's going to be equal to negative RT divided by V plus a different constant. Let's go ahead and move things up. Let's shift the constants to the same side. Let's go ahead and exponentiate so we get P by itself. That's going to be equal to E to the negative RT divided by V plus the C2 plus C, and that's going to be equal to E to the C plus C2 times E to the negative RT divided by V. Combining that E to the C plus C2 into a single constant, we get P is equal to A times E to the negative RT divided by V, in which A is the initial concentration of the pollutant, R is the rate that water is leaving, T is the time that's passed, and V is the total volume of the lake, or in our case, the cup. So there we have it. We've created a simple model for pollution leaving a lake that actually happens to work pretty well. So long as there's not a microorganism metabolizing that pollution, as would be the case if it was a fertilizer of some kind, and that the sunlight is not damaging it, and that the pollutant does not sink to the bottom or does not float to the top. And all these assumptions make the problem a lot easier. However, that doesn't mean that we can't solve problems in which those things are the case, but that's going to have to wait until next time. Thanks for stopping by, and don't forget on your way out to click like and subscribe. And also don't forget to go to mymerchoutlet.com where you get tons of great stuff, educational material, science material, and even some fashion things.